for theta, right? The Cramer-Rao bound is sigma squared CR is the joint density, basically the joint density function of all the observations, the logarithm of that first derivative squared expected value, inverse of that will give you the Cramer-Rao bound. In some cases, there may be too many unknowns. If theta, of course, is a function of x, but it also depends on some other random variable, then the joint density function is going to be a function of all this. And then, of course, I'll do an example after this. So the problem may be complicated, and in this case, we can get a sloppier bound. We call it the modified Cramer-Rao bound, as I am going to show you in this case. So the key is that the joint density function also depends on some other parameters, noise or whatever. So we are, of course, interested in, we want this one. So this is going to be, you have to integrate out n. And this, of course, you can write this as integral using the conditional density function. You can write this as in this fashion. And then if you look at this expression, d log f of x comma theta d theta, this is 1 over f of x comma theta d f of d theta. So from here, we have f of x comma theta So we have this expression just as an identity. So this is true for any density function. So this is also true for this conditional density function. So I'm just going to write it here. That I'm just going to repeat this with another density function. That's all. So you have so both will be useful, but especially we want the number 2. So if I differentiate this expression, let me call this to be 1. This is 2, 3. If I differentiate this expression, the first expression, I get dfx theta is the derivative of this, and I'm going to use the regularity condition here again. And now, let me use these two expressions. So I'm going to substitute the 2 here, and I'm going to substitute 3 here. So I get f of x comma theta d log f of x comma theta is integral f of x comma theta n or d log f of x comma theta given n d theta multiplied by the density function. But this is back to f of x comma theta comma n. So now you can write one more step, but I'm going to square this expression. So I'm going to square this expression, and which, as we did in the Cramer-Rao derivation, I'm going to write that as in this. So it's square of this, but it is integral. This f I'm going to write as two terms. So this is one term, and the next term is simply square root of f of f comma theta. Notice that this is conditional density function here. Here the density function of x given y multiplied by fo is x comma y. So I already wrote it that way. This is the joint density function of x and n. And this density function I put half here, multiply. So the integral is on dn, then squared. So we can use Cauchy-Schwarz here. Remember, so this is one expression, ax or an. This is another one, bn. Okay. So that's going to be integral a squared, integral b squared. So a squared will remove the square root. So this is going to be integral d log f x comma theta conditioned on n d theta squared multiplied by f of x comma theta comma n multiplied by integral, the square of just the integral f of, this is dn here, and here also f of x comma theta comma n dn. But what happens if you have a once you integrate this density function over n, what do you get? F of x comma theta. So this I can write it as f of x comma theta. And look at the left side. Left side is simply f squared x comma theta multiplied by d log f of x comma theta d theta squared, right? So now, of course, you see that you can write one more line. I'm going to cancel this square here with this term, Okay. So let me write the result here. So then the term you have, once you square this, we get the result, f of x comma theta d log f of x comma theta on the left side d theta the whole squared is less than or equal to integral f of integral the square of the conditional logarithm, right? D log f of x comma theta given n, this is the key, d theta squared multiplied by the joint density function of everything, which because of this I'm going to again rewrite that as remember this is f of x comma theta comma n. So the outer integral is on n, inside inside summation. So now what I'm going to do is ultimately now I'm going to do an expectation or an integration on x. I'm going to do, so this integration is on n, this integration is on x. So there is also going to be dx. So I can do the dx first and then I can do the dn. So this term is expected value but on x d, the conditional density function, right? D log f x comma theta condition known as d theta squared, and then multiplied by fn. So that's going to be another expected value. Just to remind you, the second expected value is on En, and this is just the regular expected value of d log f of x comma theta d theta squared. So you get this last inequality. But if you notice here, this is the inverse of this is the Cramer-Rao bound. So what we are saying that this is greater than or equal to 1 over, you get this identity. All the minus of the second derivative. So what's the difference? This is the classic thing, that the classical, the joint density function of the data in presence of the unknown, density function logarithm derivative with respect to theta squared. So this is greater than or equal to this bound. So this we are going to call a modified Cramer-Rao bound. So the moral of the story is, rather than find the joint density function, which may be difficult, you can condition on some of the random variables and find an inner bound, and then remove the condition through this whatever you have conditioned it on. Why do you do this? If this is too hard to compute, this may be easy. In some problems, the actual Cramer-Rao bound will be, rather than give up, you can find this modified problem. So remember, to give you a pictorial idea, says the Cramer-Rao bound is higher than the mod. So Cramer-Rao bound is here. Your variance may be here. So you are trying to find out, that's your unbiased estimate of variance. Then your modified Cramer-Rao bound is somewhere here. Because this is greater than this. So which bound is better? Anyone? Is better. But if it is impossible to get it, then at least you get the sloppier bound. But of course, if we can get a bound better than that, that would be even better than the Cramer-Rao bound. So this is, so in some cases there may be this gap. In some cases the variance is going to be here, but it's never going to be below the Cramer-Rao bound. So what is the use of modified Cramer-Rao bound? As I'm going to show in the next example, sometimes the Cramer-Rao bound is very hard to compute or simply impossible, and the modified Cramer-Rao bound is a compromising price. So that's there are other variations of it, but this is just one version. So the thing is, if there are too many random variables, you freeze some of them, find the conditional Cramer-Rao bound, then you remove the condition on that. But I proved it exactly that this will hold. The Cramer-Rao bound. So let's say the data xi or xi or ri or of the form s plus noise, signal plus noise, and the condition is signal is Gaussian with parameter theta and variance sigma is squared. Variance is known, theta is unknown, and noises are zero mean. Noise samples are zero mean with some variance. So you can later try to generalize this problem where all these three parameters are unknown. So that will be multi-parameter, and I will do that next class, the multi-parameter case. So the noise or IID, independent identically distributed. And let's say you have n samples, I equal to 1 through n. Remember, this n and that n are different. This is representing the noise samples. So I'm going to compute the Cramer-Rao bound for you, and you'll see how hard it is in this case. I mean, it involves to actually get the exact number. Then we'll do the modified Cramer-Rao bound, which you can get quite quickly, but you can see that's a sloppier result. That's the moral of the story. So in one case, I need the density function of this with respect to, these are the data. I need the data is Gaussian plus Gaussian, but these are dependent. Remember, this is just one random variable. These are IID. So, but these samples are not independent. But so if you look at the conditional density function, remember we went through this process. If you look at the conditional density function, then these are independent random variables. Therefore, given as the randomness is only from Ni, and Ni is 0 mean with variance sigma squared. So each of this is 2 pi sigma n squared e to the power minus Ri minus S the whole squared over 2n squared. So this gives the joint density function to be the product of this, right? So that's going to be 1 over 2 pi sigma n squared to the power n by 2 e to the power minus sigma Ri minus S the whole squared over 2 sigma n squared. Remember, I want to find the density function of Ri's, and Ri's are a function of theta. So I'm going to multiply the final step. I'll multiply this with Fs and integrate out S. So what I am looking for is the joint density function. I'll just write this as a function of theta is going to be f of r of so f of r theta is f of r. So that's going to be 1 over 2 pi sigma n squared to the power n by 2 e to the power minus sigma xi minus Ri minus xi over 2 sigma n squared. It's just from there. Multiplied by the density function of S. That's also Gaussian. So this is going to be multiplied by square root of 2 pi sigma s squared e raised to minus s minus theta the whole squared over 2 sigma s squared. So if I look at this is a constant without theta. Remember, later we are going to take the derivative and integrate with respect to theta. So this is a constant without theta. So I'm just going to pull the constants together and simply call it k, all the constants. Then I'm going to collect all the terms. Remember, I need to integrate out s. So let me collect all the terms. So this is e raised to minus ri squared over 2 sigma n squared. If you expand here, you have 3 terms. You have 3 terms here. Then I have plus 2 sigma Ri S over 2 sigma n squared. Then I have minus, is it? N squared over 2 sigma n squared, yes? And from there, minus S squared over 2 sigma S squared. Then plus 2 S theta over 2 sigma S squared. And minus theta squared over 2 sigma S squared. So let me call this whole thing to be K naught. Okay. So that's so that's easier to write. That's K naught. Remember, this is all in the exponent. But look at it the way I have S squared here. I have some terms involving S and some terms involving. So let me put my S squared terms together. So e raised to minus S squared is So this is my S squared term, right? I collected these two terms. And then there is S term, so this cancels, this cancels. Then the S term is sigma Ri over sigma n squared plus theta over sigma s squared multiplied by S. I'm going to call this to be mu for this, and then I have minus theta squared over 2 sigma s squared. Remember, all this is in the exponent. And so this is the joint density function of, this is also, there is S here, right? Right? Is that what you are going to say? Now, if I want to get rid of, I want to get rid of S because I want this density function. So I should integrate with respect to S, and you can see where I am going. I have S squared term and S term, so I can complete the square and make it Gaussian. Area under Gaussian is 1, so the S will go away. Right. So let me, if I call this term to be, let me call this term to be 1 over C. So what is C? C is yes, because n sigma squared this, that comes in the denominator, and okay. So that's C. Then this becomes, look at here, this becomes K0 e to the power minus 1 over 2C S squared. So 1 over 2C I'm going to pull out. I can write this as 2C mu S minus theta squared over 2 sigma S squared. Right? See, if I add and subtract a constant here, then so let me, what should I add here? Anybody? To complete the square. C squared mu squared, right? Yeah. And minus C squared mu squared. So then minus will become plus outside. Here I am going to add. And divided by 2C, this will become, effectively it will become C mu by 2. So your f of r comma theta, which we are looking for, is integral of f r comma theta s ds. So that's going to be k naught integral e to the power minus 1 over s minus c mu squared ds. That's all. And then you have e raised to minus, we just went through this. This gets divided by 2c with the minus. Minus will become minus will become plus. So outside cc cancels, you get c mu over 2 with a plus sign. And this becomes minus theta squared over 2 sigma s squared. C mu squared, right? Very good. What's the area under, what is the integral of this? By 2c, right? Is that what you see? Yeah. There was, there is 2c. So this is square root of 2 pi c, right? But c, you see, c doesn't have theta. C doesn't have theta. Now the final thing I'm going to do is I'm going to take the logarithm of f of r comma theta to find the Cramer-Rao bound, right? So that's going to be log of k naught. K naught has got this r, but it doesn't matter. There is, I'm going to take the derivative with respect to theta, it will go away. So k naught is a function of r, but then you have square root of 2 pi c. So this whole thing is square root of 2 pi c. And then you see, so you have, let me start substituting for c. C I'm going to keep it like this, c by 2 mu squared. Where is mu? Mu is here. So let me write mu as what? Sigma ri sigma s squared plus sigma n squared theta. So mu we can't ignore because it has got theta, right? So square of this minus theta squared over 2 sigma s squared. Alright, so bulk of the job is over. I'm going to take the derivative of this twice. So derivative of this with respect to theta, there is nothing here. So d log f of r comma theta is what? So this 2 and 2 will cancel when you take the derivative, right? C will remain the same, so you get a C over sigma S4, sigma N4. This is a constant, so that goes. So you just have to worry about the numerator. Derivative is the quantity sigma Ri sigma S squared plus theta multiplied by the derivative of sigma N squared. So sigma N squared theta multiplied by sigma N squared, isn't it? There's a sigma N squared here again, right? Minus the derivative of this is easy. 2 cancel, so that's simply theta over sigma S squared. So let me do one more derivative, okay? So the second derivative, then I'll do the simplification. So the second derivative of f so look here, in the numerator this will go away because this is just a constant. So the derivative is sigma n4 will cancel. So this answer is C over sigma S4, right? Minus 1 over sigma S squared. I hope I am right. We will see. So let me bring it over here. So the second derivative of the logarithm of f of, so let me substitute for C. C is somewhere here, sigma n squared, sigma s squared over n sigma s squared plus sigma n squared multiplied by 1 over sigma s4. So this cancels with this and you get sigma s squared here minus 1 over sigma s squared. And because we want the negative one, I'm going to do negative here, minus here, plus. So this is going to be 1 over sigma s squared, 1 minus this quantity. What is it? Yes? So this, if you take it, sigma n squared goes away, you get n sigma s squared over sigma s squared multiplied by, and this also goes. So we get this result to be what I have there. N over sigma n squared plus n sigma s squared. So the Cramer-Rao bound is here. Where is it? Here. So we just found the second derivative with the negative sign, right? This is the Cramer-Rao bound is either this or the second derivative. So I have the second derivative. So let me just put it here. The Cramer-Rao bound is going to be minus 1 over the second derivative of r given theta d theta squared. So if you take this minus here, we have, so expected value of this is, it's just a constant. Hello, it's a constant. So expected value of it is by itself. So the denominator is what we have. So the Cramer-Rao with the minus 1 is, look, minus 1 is already here. So this is going to be sigma n squared plus n sigma s squared over n. Yes? So if you want, I can write this as alright, so even in this simple problem, we had to go through all this. Whereas if you try to do this, this is very easy. So let me do the easier part now. So any questions? This is the Cramer-Rao bound. Huh? This one? Sigma n squared. Yeah. So suppose, I mean, even in this problem it took this much. But suppose now you say, let me condition it on, so let me do it this way. So remember, Ri is S plus Ni. S is normal with mean theta and variance sigma s squared. So you can write S certainly as like this, right? Where Wi is normal with mean 0 and sigma s squared, right? Look here, if this is mean 0 with so the randomness is not from here. If this is random, because there's a random component which is Gaussian, this is unknown constant. So you can write it in this fashion. So if you want, you can rewrite this problem. Not I, there is no I, there is S is just one S. In other words, on all the noise observations, it's the same randomness. So these are independent, but this is not independent. This is a random variable plus random variable, will be a random variable. But then W plus N1, W plus N2 won't be independent. So for that now I am going to condition it on W. And then I'll use this, so I'll use this result. So I don't have to write all this, because we wrote all this, we can. So of course the joint density function of Ri and theta given W would be, see if conditioned on W, this will be normal with mean theta plus W and variance equal to sigma n squared, right? Yes? So that's going to be 1 over 2 pi sigma n squared, square root, e raised to minus Ri minus theta minus W the whole squared over 2 sigma n squared. So let's find the, so we are almost here. Let's find the joint density function. So if you don't want to go through all this, or in some cases it is not even possible to do this exactly, then we can do this. From here the joint density function is the product of the density functions, because given W all these random variables are independent, same argument. So this is 1 over 2 pi sigma n squared to the power n by 2 e raised to minus Ri minus theta minus W. So let's take the logarithm. So that's going to be log here plus log here. So that's going to be simply this one, right? Log of this is minus this. So now let me take the derivative of this with respect to theta. So this is goes away. So that this is going to give me 2 cancels. Minus cancel, so you have sigma Ri minus theta right? So let me take the derivative one more time. So that's going to be, look here, this goes away, it's simply going to be minus n over sigma n squared, right? So from here you get the sigma squared m modified Cramer-Rao bound is minus 1 over the second derivative, or you can take the square and go through that also. And you have to do one more expected value, but that's already a constant. So that's going to be this sigma squared over n. See, in the previous case, you had all this extra component. So you are not going to guess this unless you go through all this. So you can see this is smaller than the Cramer-Rao bound, which turned out to be sigma n squared. I just wanted to compare that this is 1 plus something, n sigma s squared over sigma n squared. So you have more here. So this is what I mean by you just have to go through the derivation. Now you can go, so if the actual Cramer-Rao bound is hard, then you can do this modified Cramer-Rao. So for example, you should try, I'll try to make up some problems on phase modulation and so on. Most likely the computing the Cramer-Rao bound is going to be hard, and the modified Cramer-Rao bound by cleverly. So remember, this is the freedom is up to you, which random variable you want to freeze. So then you unfreeze it here. But of course, if this quantity turns out to be a constant, then this expectation has no meaning. It's just one expectation is the same as the double expectation. So it's a sloppier bound, but but most of the time faster, right? And but because it is sloppier, it may not be much useful. But if the Cramer-Rao bound is impossible to compute, then you have something. That's the whole point.